Thank you. Now let's take a look here. So this is going to be rotating on the y-axis. Let me ask you this. So this is where you start. This is the first thing you want to memorize. If you wanted to use washer method, it would be integral, crap to worry about later, d what? So if I want to use this method, let's figure out if it's washer or not. Integral stuff d what? Yeah, dy, because I'm rotating around something parallel to the y-axis, namely the y-axis. So that's the one that the d stuff is directly the same thing as the axis around which you're rotating, or it's parallel to. What would this mean if you wanted to use this method? What would this mean you'd have to do first? Solve for y. All right. So if I wanted to use shell method, that allows me to do integral stuff dx. If my rectangles march along the y-axis, which is what they would do here, they create disks. If my rectangles march along the x-axis, they create shells. That's one way to look at that. The really, really, really nice thing about shells, if you draw in a representative, so let's look at this. That's got a few nice things. They're already functions of x. What do I need to know for shell? So I'm going around the y-axis. I'm going to use this version of it. I've already got function of x. Now watch. This is the first little adjustment to this general rule. This is going to be the height, right? This is the height. Now, if it hugged the axis, the height is equal to the function. This doesn't hug the axis, does it? I mean, here's the area I'm rotating. Draw in a representative rectangle. How tall is that?
The top function minus the bottom.
Beautiful, right? Which feels a lot like 6-1, the area between two curves. That's how I would figure out this area by itself, is I do the top minus the bottom. So here the height is square root of x minus 1 minus x minus 1 squared. That's the height. Okay, I like it. So we got that piece figured out. Now the radius, now here's the thing I didn't really spend a lot of time on, but the radius is only going to be x here if I am rotating around the y-axis, because how far away from the center, which is the axis of rotation, is one of these rectangles? How far away is that? I love to get your eyes are like, how the shit would I know? I had my rectangle in a different place. But where is this? It's at some x place, right? It's not x plus 1. If I rotate it around x equal negative 1, wouldn't the radius then be x plus 1? If I rotate around x equal to 1/2, it would be x minus 1/2. But since I'm rotating around the primary axis, then the radius really is just the variable x. It's how I get to any rectangle. How do I get to any rectangle? I go out x far to get to that rectangle. That's the radius. That's from the center of the shell. So what do I got so far? I got, what am I integrating from to? Why am I using the worst pen? Come here, green. You are the best at the moment. What am I integrating from to? What's controlling things? We figured out dx, right? X is controlling things. We'll use shells. So from 2 is going to be controlled by the x. And I got more detail on there, right? You should, yeah, 1 to 2, right?
Yeah.
And that's just from setting these two equal to each other. Or just realizing 1, they're both 0, and 2, they're both 1. Yay. Is that cool? That's that whole point about, that's just like 6-1. A lot of this is going to feel a lot like 6-1 because we are taking areas between functions sometimes. We're just rotating them now too. But there will be a piece that feels like 6-1. All right, so what do we got? Let me pull the 2 pi out here. There's my x times f of x. And what did we say the height was? And actually it's not f of x, but it's the height in general. So it's not going to be this business here. All right, now, does that look like something you would want to do? You could do it, but this is where you go, okay, shells, let me just put you in the corner for a minute. Let's try to set it up as disks instead. Maybe you can see why I picked shells first, because I knew we were going to get to a point where, like, well, I don't want to do that. This is part of the process, is to set it up until a point where you go, oh, okay, that's disgusting. Let me backtrack and try the other method. That is a part of mathematics. The first place you hit that is when you do trig identities. Let me try this, that didn't work. Let me try to start with this side, that didn't work. Let me choose a different identity, yay, it worked. A part of it is realizing the choice you made was wrong. We have no way of knowing that ahead of time sometimes. This is gross. Not impossible, but gross. So what would this look like if I chose disks instead? Let's do that. And maybe we'll call it a day. Let's see where we get to. Maybe not. We'll see. So I chose disks instead. It would have to be integral dy, which means I would have to solve these for y, which isn't as difficult as you might think. I don't know how you feel about it. How do I solve each of those for y? This one's not too bad. Solve it for y. Yeah, y squared plus 1, so you get x equals y squared plus 1. And what about this guy? Solve this for x. Yeah, you don't have to worry about plus or minus because this is obviously the positive part of it. Right? So I get square root of y plus 1, right? So that is something I want you to realize right now. That's why I say the first thing to pick, when you pick your method, you write down what's going to be right here, because that's going to control like everything else. It's going to remind you to look at that axis for these. It's going to remind you what everything in here has to be in terms of. That's why you start here. Depending on which method you use, it's going to tell you dy or dx. So let's see what's going to happen here. So what do I need to determine now? I probably have to draw this over again. Oof. There's a little much going on. Let's see if I can do this quickly. 1, 2. So there's the area we're talking about. This is now y squared plus 1. This is now square root of y plus 1. Okay, so, and now it's going to be integral dy. Is that cool? That's the disk method. It's got to be dy. I'm rotating around the y-axis, so it's got to be dy. So what are my rectangles going to look like now? When I draw them in. They're going to march along the, which axis? The y-axis. So they're going to look like, not like that, they're going to look like this. So now I need to figure out my inner radius, my outer radius, right? So the general idea is going to be pi Why do I keep going back to you? R outer squared minus R inner squared. So what's the inner radius? You gotta draw a couple maybe just to make sure you're getting it right. What's this height determined by? How far away am I? Y squared plus 1. That's where you stop. That's the wall you stop at. That's how far away it is. Y squared plus 1. If y is 0, how far away is it supposed to be 1? It is. Okay. So that's going to be the inner radius is y squared plus 1. So the outer radius is going to be square root of y plus 1. Who got it? Square root of y plus 1. There you go, buddy. Now let's see what this integral looks like now. So dy, what's y doing? Going from 0 to 0. See, now this is interesting. X is going from 1 to 2. Y is going from 0 to 1. So it goes from 0 to 1. That's what y is doing. R outer squared, that'll be square root of y plus 1 square minus y squared plus 1 square. While that's not the prettiest thing in the world, it is much better looking than that was. See, the one thing that shells very often is a really nice way, but the one thing it has going against it is this little extra x thing that it's got. That's the radius, 2 pi r times the height, right? See how that made this worse than it really had to be? X times square root of x minus 1. Which still, again, not impossible. You use u sub, you could do that. So here, you guys pick a way to do it. Do one of these two. Finish it out. I'll probably do that one because I have a feeling less of you are going to do it that way. So this would be let's see. God. 2/5 and 2/3, it's 16/15. So 15 plus or minus, whatever the hell that is. Let's see. 11 1/2 minus 1/4. 24, so that's 5. 5 minus 14/3. So really? 1/3? So minus 2 pi over 3 equals 10, 20. I get 22 pi over 15. Let's see if that's true. How are you guys doing with this one? If you're doing this one, or are you guys just like, let's just wait till he does it. He's going to do both ways. So this one's not too bad. You fall this out, you get y plus 2y to the 1/2 plus 1 minus y to the 4th minus 2y squared minus 1. Ones go away, that's nice. That's about it. So you get pi times y squared over 2 plus, let's see, that'll be 3/2, 2/3, so 4/3 y to the 3/2 minus y to the 5th over 5 minus 2y cubed over 3 from 0 to 1. Check. So it's a big fraction problem. 0 makes everything 0. That kicks ass. So I got 1/2 plus 4/3 minus 1/5 minus 2/3. I'll be such a happy person. This actually comes out to be that. So let's see. I got 4/3 minus 2/3 is 2/3 plus 1/2 minus 1/5. Let's see. 4, 7/6. 7/6 minus 1/5. That's 35 minus 6. Oh, I get 35 minus 6. I get 29 pi over 15. I'm so close.
That's what I got.
29 pi over 15. So over there, I probably just made some stupid. It's pretty close.
Actually, it's over 30.
30? Yeah. Let's see. Yeah, 35 minus 6, 29 30ths. Yeah, okay. So over there, I wonder what I did. I probably just did something too quickly. Oh. Yeah, they should come out the same way, but there, I probably just made a quick, stupid mistake. Oh well, let's see. 16, 15, 32, 5, 16. All right, I can't see it right now. Oh well, it should work out either way. This way was definitely easier. I didn't need any u-sub steps, right? So there's nothing wrong with getting to a point where you set up the integral and you go, well, let me try the other way. Because I don't want to deal with that shit. There's not a damn thing wrong with it. There will be a few problems where you cannot do it a certain way. If they give you a function you can't solve for x, and you're supposed to go around the x-axis, you can't do disk method. Let me see which way. So if you want to revolve around the x-axis, disk method would say you have to integral dx. So if you can't get your function in terms of x, you can't do disk method. So there will be something like if they say y equals, sine of x minus x squared. Can you solve that for x? No. So then I wouldn't be able to do it where I'd have to do it with dy. But this, if it's like this, I definitely want to do dx. I have to. So I have to use the method that allows for that. So that's why that's the first place you go is, if I do this method, is it dx or dy? You write that down. That controls everything else. That controls the limits. That controls what this is supposed to be in terms of. So forth. And there's nothing wrong with writing out the entire integral and then going, wait, that's ugly. Let me try the other way. Sometimes it's just a part of the problem. There's no way to know everything ahead of time, unfortunately. So 6.2 is the washers and the discs. 6.3 is the shells. Let's see what time we got. Look on the back of this real quick. And this will be the last thing we do. let's just do, can you sketch the region I'm talking about, that first little grid there? Can you sketch the region I'm talking about there? Do it with you. So it's the region bounded by those equations I give you. Now just sketch it first. I have to take it. Well, I do have a picture of that. Because this is really important. This one says x equals 2 is one boundary, right? So it kind of gives you a clue as to how far to go with the x squared. When x is 2, y is 4. So that tells me to do that far. And then, so that's one wall. This is another wall. And then where's y equals 0? That's another equation for the x-axis. So this is the region I'm talking about. Now real quick, if I would have said y equals x squared, x equals 0, and y equals 4, that would have been this region. Y equals 4 is one wall. X equals 0 is an equation of the y-axis. That would have been this region. Completely different regions. I mean, they're both like related to each other, but one thing to be careful about is when you draw the area they're talking about correctly. Because if you can't, everything else is going to be shit. I don't care if you do everything else perfectly, you've started with the wrong shape. And you're rotating something freaky. So this is the one that's on the paper. If it was this, it would have been that piece of it instead. Now, if I rotate it around the x-axis, then which method am I going to use? Yeah, if I want to use this method, why is that kind of nice? Because if I use this method, what's going to go here? Dx. So I can leave everything the way it is. Now I've got to figure out which way are my rectangles going to be. If I draw in a rectangle, what would it look like? Is it going to be lying down like that, or is it going to be standing up? Yeah, glued to the x-axis. It's going to have to march along this, so it should look like this. So when I rotate it, I get my discs. So every step kind of leads into the next step. What's really nice about this method here is, see how this hugs that x-axis all the way through? There's no inner radius. That's when this method is even nicer. You don't have to worry about a second piece to it. So what's my r going to be? What's my limits here, first off?
0 or 2.
Yeah, 0 to 2. It's all about what x is doing. So 0 to 2. And now I need r squared. What's my radius going to be? X squared. And of course that's going to be squared. That's the easy piece to forget, especially when there's already a power on this thing. Whatever the radius is, it's got to be squared to make pi r squared. And then this is a nice, easy integral I got, right? I like it. Oh, yeah, okay. So let's do this. Look at the next one. And then this is the last thing I think we'll do today. The next one's got the same exact setup, the one that's next to it over this way. Y equals x squared, x equals 2, y equals 0. So it's the exact same region, except now I want to go around y equals -2. Does that change the method that I want to use? I can still use the same basic method. I don't really separate discs and washers as two different methods. They're one method. One has two discs that you subtract. Ooh. Right? This is still parallel to the x-axis, right? So if I wanted to use discs, I can. Integral dx. But now I'm going to have, the only difference really is I'm going to have what happening here? Well, two things. What's my outer radius going to be? No. X squared plus 2. The radius is always from the center, and the center is the axis of rotation. So see, everything I'm doing, I'm not drawing any 3D at all. I want to get away from that. I want to try to draw a little bit of 3D, but you don't have to. What's the inner radius going to be? 2. I love it. So then you got x squared plus 2 squared plus 2 squared. Yeah, plus minus 2 squared. So r outer squared minus r inner squared. Remember, it really is pi this r squared minus pi this r squared. That's how you get just the amount that you want. Subtract this part out. And that would be a relatively simple integral, right? Okay, I like it. So we laid a lot of groundwork out. So what's going to happen on Monday is I'm going to have the answer key for the practice test. We're going to firm up 6263 first. Probably the first half of the class I'll be doing examples. And then the rest of the class will be devoted to review for the test the following day. We'll take the test on Tuesday. I will somehow make sure to have it graded for you by Wednesday so that you have it to make corrections to and study from for the final. It's going to have an offering. So probably Monday I'll have the practice final for you. And on Wednesday I'll have the answer key for that.
So the test is going to be from 4.9
4.9 through 6.5. Bullshit. Remember, we didn't do 6.4. Right? And chapter 5 has 5 sections in it. Not as horrible as it could be. It's just all of integration. That's all it is. All right. See you guys next week. Can we take tomorrow off?
Can I get that, please?
Yeah.